All right, guys, welcome back. So this is lesson 3.2 about our basic derivative rules. So while we're going through this, we always want to keep in mind what a derivative is. So remember from last lesson about the definition of a derivative, the mathematical notation for it was that limit is h approaches 0 of f of x plus h minus f of x over h. Really what we need to remember about the definition, what a derivative really means, is it's the instantaneous rate of change of a function. And remember that we can see that graphically as the slope of a tangent line. So we're going to kind of keep that definition in mind while we look through some of these basic derivative rules. So let's get cooking talking about some of these basic rules. So the first one is the derivative of a constant. And derivative of a constant is always 0. And this is one that really makes sense intuitively when you think about what the definition of a derivative is. If the derivative is the rate of change of a function and that function is just a constant, then the rate of change of that will be 0 because that constant is never actually changing. So if f of x equals 3, f prime of x is equals 0. F of x equals 7, f prime of x equals 0. This one sometimes throws people off because they see pi, or if you see it written as pi. Remember, pi is also just a constant, 3.14 and a whole bunch of other stuff. So f prime of x of pi still equal to 0. So anytime you're taking the derivative of a constant, you get 0. So next one is the power rule. So power rule, a couple of you guys, when we were doing those derivatives by definition, we were doing the whole limit notation, you may have caught on to a pattern that happens when we take derivatives of polynomials with powers. So the power rule, basically what this is saying is if I have a coefficient, I'm going to multiply the coefficient by the power and drop the power by 1. So this right here is the mathematical description of the power rule. This notation, d dx, is another way that you may see written that says d dx means take the derivative of whatever this function is with respect to x. So let's just say, for example, that I wanted d dx of x cubed. So the way I would do this is I would take the power, multiply by whatever my coefficient is. My coefficient here is 1. So this would be 3 times x, and then drop the power by 1 to the 3 minus 1. So this would just be 3x squared. So we've got a couple of examples down here of the power rule where the coefficients are not 1, but the same idea still applies here. I just take the derivative, or I'd take the coefficient, multiply by the power, and then drop the power by 1. So for example, the derivative of this first term here, if I wanted the derivative of this would be 5 times the power, which is 3, times x to the 3 minus 1. And now we're actually going to talk about a rule in a second. This is sum and product rule, but basically, if I'm adding or subtracting terms, I can take the derivative of those terms individually and then add or subtract them. So the derivative of this next term will be 12 times the power, which is 2, times x to the 2 minus 1. And then this last term, I noticed this last term is a constant, so that derivative is just 0. So then when I simplify this, this would be 15x squared plus 24x. If we notice, 3 times 5, 15, drop the power by 1, 15x squared. 2 times 12 is 24, drop the power by 1, 24x. So I can still apply the same thing here. This would be negative 20, 5 times negative 4, x to the 4th, plus 3 times 2 is 6, x to the 1st, drop the power by 1. And now this one I have here because remember, if I have negative 5 over x squared, I can rewrite this as minus 5x to the negative 2nd. If I write this as negative 5x to the negative 2nd, then I multiply. Negative 5 times negative 2 is positive 10. This is plus 10x to the negative 3rd. Negative 2 minus 1 gives us negative 3. So I want to do one more example with that because that sometimes seems to throw people off when I have fractions. So just remember, if I have f of x equals like 3 over x squared minus 2 over x plus 3, I could rewrite this using the definitions or using the properties of exponents. This would be f of x equals 3x to the negative 2nd minus 2x to the negative 1st plus 3. And now I can just apply the power rule. So then f prime of x would be equal to negative 6 x to the negative 3rd. We multiplied the coefficient by the power, subtracted 1 from the power, plus 2x to the negative 2nd. Multiply negative 2 by negative 1 gives me positive 2. Subtract 1 from negative 1 gives me negative 2. The derivative of this constant is 0. So this is my derivative. All right, so our next rule, we actually just applied this a second ago. It's the sum and difference rules. A lot of people do this intuitively, and that's fine for when you're taking derivatives. You can take the derivative of each term individually and then add the derivatives up. So this derivative would just be 4x plus 6. All right, because we just applied the power rule and then took the derivative of this term, 4x, derivative of this term, 6, the derivative of this term is 0. All right, so next up is the product rule. So unlike sums and differences, the product rule is not just the product of the two derivatives. So this is the mathematical notation. The derivative of uv, u times v, is equal to u times the derivative of v with respect to x plus v times the derivative of u with respect to x. Basically, the way that I like to remember this is 1d2 plus 2d1. So I take the first term. So if I want the derivative of this right here, I would take the first term, x squared plus 3, times the derivative of the second. So the derivative of the second, this would be 6x squared, power rule, plus 5. All right, so I've got 1 d2 plus, I'm going to take the second term, 2x cubed plus 5x d1 times the derivative of the first term, the derivative of that term, if we apply the power rule, would just be 2x. All right, so that is the product rule. 1d2 plus 2d1. Next rule up, quotient rule. So the quotient rule, here is the mathematical explanation. So if I want the derivative with respect to x of u over v, I would take v times the derivative of u with respect to x minus u times the derivative of v with respect to x over v squared. All right, this is another notation. If we know that everything is with respect to x, then we can just write this as d of u over v equals v du minus u dv over v squared. So the way that I like to remember this is that this is low d high minus high d low all over low squared. So when I apply that here, I take low x squared plus 3 times d high, so the derivative of the numerator. So that would be 6x squared plus 5. Again, power rule. Power rule is going to be your best friend. You're going to use it all the time. So you've got low d high minus high. I'm going to take what's in the numerator, 2x cubed plus 5x d low. So the derivative of the denominator, which again, power rule, coming in clutch again. That's 2x. And then all of that is over low squared. So it's over x squared plus 3 squared. All right. I know that we're running through these rules pretty quick in this video, but again, benefit for you guys is you can pause this video, go back and watch this as many times as you need to. So that is the quotient rule. All right. Next, we're going to talk about a few derivatives of trig functions, and these two are by far the two most important ones you need to know. So the derivative of sine is cosine, and the derivative of cosine is negative sine. So these two, commit them to memory. In class, we're going to use these two to find the derivatives of the other four trig functions. So tangent, secant, cosecant, and cotangent. But right here, we're just going to practice the derivative of 3 sine of x. This would be, so you're going to multiply this constant by the derivative of sine of x. So actually, let's back up a second. I could technically, what I could do here is I could apply the product rule. And I could say 1, so 3 d2, so the derivative of sine is cosine, plus 2 sine of x times d1, the derivative of 3 is just 0, and I get 3 cosine of x. When you have something like this, there's another rule, it's called the constant multiple rule. If I'm multiplying a function, sine of x, by a constant, then I can just multiply the derivative of the function by the constant. So because the derivative of sine is cosine, I can just write that this derivative is 3 cosine of x. All right, so then we are also going to look at derivatives of exponential functions. So if I take the derivative of a to the x, this is a to the x, same term, times ln of whatever the base of the exponential function is. So there's a special case of exponential functions, and we're going to use this definition right here to show this special case. So if I want to find the derivative of e to the x, so if I want d dx of e to the x, using this rule right here, this would be e to the x, same term right here, times ln of the base of the exponential function. So this would be ln of e, and we know that ln of e is just 1, so this would just be e to the x. So this creates a special case for exponential functions. So the derivative of e to the x, d dx of e to the x, is just e to the x. All right, then we can apply the same rule with different bases and it would still work out. We just have times ln of something. All right, so last one that we're going to talk about is the derivative of a logarithmic function. So if I have the derivative with respect to x of log base a of x, it's equal to 1 over x times ln of a, where a is the base of whatever this logarithm is. So again, this is going to create a special case for logarithmic functions when we deal with ln. So if I want d dx of ln of x, this would be equal to 1 over x times ln of the base of this logarithmic function is e. And again, we know that ln of e is just 1, so this is just 1 over x. So it creates a special case for logarithmic functions. All right, and just so we can see how this would look with something else, let's say that I wanted the derivative of log base 3 of x. So if I wanted d dx of log base 3 of x, we would do 1 over x times ln of 3, because 3 is the base right here, and then that would be the derivative. All right, so thank you guys for sticking in today. Today was about some basic derivative rules. Again, I know that we went through those fairly quickly, but go back, watch the video, pause, look at any rules you need to. In class, we will do plenty of practice with these. But if you have any questions, bring them to class. And I hope you have a fantastic day, and I'll see you in the next video.